Hi, I'm Dr. Adam Teman of the EnICS Labs at Bar-Ilan University. And here we're going to start the third part of our Digital on Top Physical Verification lecture. And at this point, we're going to translate the Verilog netlist into SPICE. So as I remind you, what we did in the last two lectures, we first showed a general overview of our LVS process, and then we showed how we extract the Verilog netlist, fixing all kinds of problems. So we now have a Verilog gate level netlist. So the next step is that we have to gather our CDLs. Remember that a CDL is just a SPICE netlist. So Innovus has provided us with a gate level Verilog netlist, but LVS runs on SPICE netlists. Okay, where do we get the SPICE netlist from? Well, they're part of the library. So in every standard cell library, we should have a directory called CDL or SPICE or something like that, which will have a file or several files that have the SPICE net lists of each and every one of the gates. The same goes, of course, for every other IP that we have. We should have a library that comes with each IP, and it should come with the CDL or the SPICE net list of each of these things. But why do we want to use the CDL file? The CDL file doesn't have the parasitics. It doesn't have all kinds of diodes and capacitors and resistors and so forth, which will actually cause, in many cases at least, LVS to fail. So we don't want to have the post-layout parasitics. We just want to have the kind of clean pre-layout type of a netlist to compare with what we have in the layout. Okay, so we need to create an include file that references the CDLs of these things, the standard cells, of course. So we have something like .include path to standard cells, the IOs, something like .include path to IOs, the compiled memories, .include path to SRAM1, SRAM2, etc., and any other hard macros we have, such as .include path to custom block. Again, we can also run, if we're running a type of a hierarchical like bottom-up flow, we can also add the hierarchical soft blocks that pass LVS standalone, but it's actually really, we should probably flatten this for final LVS to make sure there aren't any problems with those CDLs that were actually generated if we have the data. We can't do that with these type of custom blocks, but we can do it with soft blocks that we designed them with a place and route tool. They actually have just a regular Verilog type of a netlist, so we should really flatten everything out and do it flat at the end to make sure we don't have any problems. Okay, so now that we've collected all of our CDLs of our SPICE netlist, we can run V2LVS, which I mentioned many times in the last two parts of the lecture. Okay, so V2LVS is a mentor tool. V is for Verilog, 2 is to translate to, and LVS is what we're doing now. Other vendors have their own tools. I'm just going to show you it with the mentor tool that comes with Calibre. So V2LVS we run with all these different types of options. Okay, and basically what we're saying here is that this is the Verilog netlist that's going to come as an input to V2LVS. This is the CDL that we're going to output from the tool, and we have some sort of an includes file that we mention it here, which is all this collection of these CDLs that I mentioned on the previous slide that we're going to include along with the Verilog netlist to create one CDL file, which is going to be our source netlist. But as usual, in addition to the problems that we mentioned in the previous part of our lecture, there are a bunch of problems that can happen here. We may have duplicate subcircuits, we may have globals, we may have bulk connections, we may have ports that are shorted outside the block, different types of things like that. So we're going to start with problem which I call 1A, and that's duplicate subcircuits, but in custom blocks. So now this is some sort of a hard IP that we got from some vendor, and it's going to have duplicate subcircuits inside. What does that mean? When creating a block, we may have a cell with the same name as a cell in some other block on the chip. So we have this is block 1 and this is block 2. They're both custom blocks, or maybe one of them is a non-custom block and one of them is a custom block. But in any case, they both have instantiated some sort of a cell inside, and we called it INV for inverter. And we just did it because that was the name we gave it. But now we have two inverters in the design, and now when we flatten everything out and connect everything together, we're going to have two subcircuits called inverter, and that's a duplicate subcircuit, and we can't live with that. So the first solution is this. In Virtuoso, we should give custom instances a unique name by adding a prefix or a suffix. So we should rename our cell inverter to myblock_inverter. And assuming myblock is going to be something that's kind of unique to this block in the design, we won't have this problem afterwards. Solution number 2, we can post-process our CDL. As I told you before, post-processing is not a great thing to do, but we can do that. We often have to do it, especially if we are not in charge of these IPs and we just get them and there's this type of a thing. Then we can post-process them by adding a suffix or a prefix. And here's a short script that will do this. It will actually go over our entire SPICE netlist, and it will find all the module names and add some sort of a suffix to all of them. So that's another option. There are other options inside the custom flow where when we export our CDL, we can add some sort of a suffix or prefix, but I'm not going to go over that right now. So a similar problem, and that's why I call it 1B, is duplicate subcircuits, but now inside our digital blocks. So now we're going to do a bottom-up hierarchical flow. For example, we're going to have some sort of a big design over here, and inside we're going to divide it into partitions, and this we're going to this and this and this are all going to go through a separate place and route flow. And now each one of them decided to have, again, a subcircuit called inv or something else called block 1, block 2, and so forth. And this is going to actually happen often. For example, if we're using Genus to synthesize, it's going to give some sort of name like GNS123, and you're going to probably have GNS123 in this block, and this block, and then we're going to have a problem with duplicate subcircuits because they're actually completely different modules. So in solution number 1 is tell our synthesis tool. In this case, we're using this cadence flow, so we're using Genus, but it's similar to other tools. We need to tell them to give our modules a unique name. So how to do it in Genus is set attribute gen module prefix my block, and it will add my block as a prefix to each one of the modules that it creates. Solution number 2 is actually to tell Genus to rename the modules before it exports them. So we can do something like this. For each module, get db modules. It will return all the modules to us, and then rename object. We'll add this prefix of my block to each of the modules. If we got our design already synthesized and it already has this stuff inside, we can tell EnICS to change the module names before Netlist export. So we do update names minus module minus suffix or prefix my block, and that will change all the names of the modules to have this suffix or prefix. So these are kind of 3 ways that are a bit independent that can be applied to do it. Solution number 2, of course, is to post-process your CDL. Actually, the script that I showed on the last slide will give subcircuits unique name by adding a suffix or prefix or something like that. So the same type of thing, but we should really do it, if possible, inside the tool and not as a post-processing step, which is, as I mentioned before, dangerous. So we have to get rid of our duplicate subcircuit names. Second problem we have is globals, and this is a huge problem. Okay, a global signal in SPICE .global. Unfortunately, in the SPICE kind of a definition, this propagates to the entire design and takes priority over local signals with the same name. So I want to clarify this because this is really bad. Okay, if we have something like this .global VDD in one of the files, and it can be the file in the smallest type of subblock that we're using, that means that every place that it says VDD inside is used inside the entire design, it's going to be shorted together. Okay, that's really, really bad, especially for something like VDD, because let me give you an example of what happened before. We had in what I drew kind of in a previous part of the lecture, we had 2 different power domains, okay? And inside the power domains, we had a standard cell, and the standard cell had pins, VDD and GND, and inside here it used VDD for something right inside, and here it also had, it's the same standard cell, so it had VDD and GND, and VDD and GND were used inside this cell. But this net was called my VDD1, and this net was called my VDD2. And they're different voltages, they're different, they're completely different. But now what this says is that if I have inside my standard cell definition, I have this thing that says global VDD, okay, that means that this VDD is going to connect to a net called VDD. And this VDD is going to connect to a net called VDD. That means this and this are practically going to be shorted together. We're going to have problems running our LVS. Nothing's going to work. Okay, so globals are really bad. And the solution to this is do not use global signals. However, unfortunately, we often get vendor-provided type of blocks, and sometimes we will accidentally get CDLs that have globals inside. For example, a bunch of IOs that we use for 65 nanometers, they do use global signals. So, for example, at the top part of, at the first line of the CDL file for these IOs that we have, there's this .global, VDD, VSS, VDD, PST, POC. This is a vendor-provided CDL file, and it essentially shorts together all of these signals inside our design, which is something we really didn't want to do. We had a whole bunch of different VDDs, a whole bunch of different power domains, and this is really a huge pain in the neck. Just removing this line, it's not enough. Okay, it's going to leave us with many problems. So in the CDL, we don't have port connections to the relevant subcircuit. So for example, we have some sort of cell inside, right? And it has, say, if it's an IO, it has a ring here that has VDD, but there's no connection to VDD inside this cell. Okay, it's just assuming that it's a global, so it may have a transistor here or something like that that's getting VDD, and it just uses the name VDD. But in the CDL, it says subcircuit. Okay, and it has a list of the things A, B, C, but it doesn't have VDD in it. So when we use inside here, M0 has VDD inside the subcircuit, it doesn't know what VDD is. So what we have to do is add VDD to the port list. Okay, now once we added VDD to the port list, okay, the Verilog netlist has to get VDD as well. But how does Innovus or whatever know that it has to connect VDD when it wasn't included inside the left lib of this IO at the top level? So we have to somehow do it there. And the left, again, I guess the left will solve the problem of the Verilog netlist, but we have to tell the tool that this hidden VDD rail over here exists and it should be connected to the next VDD rail, which is connected by abutment. But that doesn't appear inside the left that was provided by the vendor, and this is really going to cause us a headache. Okay, so the real solution to do it, we're going to have to just modify the left in the CDL of the IOs or of what the vendor gave us. If you don't want to do that for some reason, or if you want a quick and dirty fix, what you can always do is do some post-processing, and this can work, but it again is not a recommended flow. You should really fix the lefts and CDLs. If you can, you should ask your vendor to provide you a fixed version that supports this type of a multi-VDD flow. I'm assuming that in many of the advanced processes, this is already fixed because we assume that we have many power domains, and this shouldn't happen. Problem number 3, bulk connections. Okay, so the issue is that a transistor has a bulk terminal. You know, that thing that connects the body of the transistor to somewhere. Okay, standard cell lefts, however, may not have a bulk terminal, and I'm basing this on some standard cell libraries that I've worked with. Okay, there is no connection to the bulk for gates in Innovus, in our place and route tool, and the export Verilog netlist has no bulk connections. Again, if we don't have the connection, just like before with the connection to VDD in that internal power rail inside the IO, we're not going to get our export to Verilog to have such a connection to this tool. And then when we run V2LVS, we're not going to have any connection inside the cell. It will just show actually that we have some sort of a net with some sort of a name that's connected to the bulk of the transistors. And that's a huge problem, especially with something like standard cells where fixing it manually is going to be really tough. Okay, so this leads to 2 major problems. The standard cell SPICE CDL views have to have bulk connections. They have to. I mean, there's a bulk connection on the transistor. It has to be connected to something. For example, VPW or something will be connected to VPW and VNW to VNW or something like that. It may be automatically defined as VDD or VSS, but that's not so great because what if we are using bulk biasing or something like that? So this is really strange because it means that the CDL has 2 extra ports that we don't have in the gate level netlist. So the Verilog netlist didn't have this VNW and VPW connection, but the CDL does. So what is V2LVS supposed to do? What's it supposed to connect to those 2 extra connections? You can't have a Verilog netlist that has a Verilog module instantiation that has a different number of ports than the CDL representation. If we would globally define a bulk connection to VDD and ground, this wouldn't support power domains, body biasing, special power nets, etc. This is a really hard thing, and it was very common in older designs. It may be solved in a lot of the newer standard cell libraries. So how do we solve this? Well, V2LVS has an add pin option. So if we do V2LVS and add this minus add pin VPW minus add pin VNW, what it's going to do, it's going to add VPW equals VPW and VNW equals VNW to the netlist that comes out. But this is also not a good solution completely, because we're connecting, again, this pin that we know it was called VPW, that's why we wrote VPW. It's just connecting it to a global net, or a net that's at a higher level, that's called VPW. But is it connected to VPW? It might be connected, well, it probably is connected to VSS or to VSS2 or some other pin. And this VNW is probably connected to VDD or VDD2 or something else. And so we have to connect VNW to VDD2 at a higher level inside the SPICE netlist, and that's something that we're going to have to somehow take care of. Not necessarily easily. We might have to do it with post-processing. So this is a solution, but it is not the best solution. It may be okay for a single bulk bias, not if several bulk biases are used. It really can give you trouble. So the solution is either post-process the CDL to connect the correct VPW and VNW to each block. Again, that's not a great solution, but it does work. But it's much safer and better. Modify the LEF, add this connection to VPW and VNW, so you have it in your Verilog gates that are spit out of the place and route tool, and you get the correct connectivity. Problem number 4, shorted ports. Okay, so I mentioned this before. Sometimes ports with different names are connected to each other, either at the board level or even for macro level LVS. Okay, for example, if we have a separate VSS bulk connection, but they're connected through the substrate to propagate VNW, VPW signals from the previous slide. Okay, so this is something that is sometimes done. You may have two different connections. You may, again, want to have VNW and VPW because you use that add pins type of thing, but how do you connect VNW to VDD and VPW to VSS? Okay, so the first solution is use that SPICE keyword star.connect that I mentioned before. So if we do star.connect VDD VNW, that should connect the VNW to the VDD pin. Make sure that the order is correct here. So the VDD that comes first, VNW second, because that means that we just propagate VDD throughout the design. If we would have made it the opposite way, then VNW is propagated throughout the design, and that for sure is going to cause us a lot of headaches. Okay, but this is, again, a post-processing kind of solution. It's adding this star.connect to the SPICE netlist. It's not something you want to do. A better way, the recommended way, make a wrapper that connects the two nets that run LVS on the wrapper. So in other words, we have our design that was spit out of Verilog. It's called my design. Let's call it D.V. Okay, and it has a pin here for VDD and a pin here for VNW. And these are actually shorted together, right? So the star.connect will short them together. But instead of that, we should make a wrapper on top of it. And the wrapper will just have one pin that's for VDD, and it will connect VDD to both of these, and we run LVS on the wrapper. So this is d_wrap.v. So all it does is it connects everything that's outside to everything that's inside on a one-to-one type of a connection. So if there's a pin A here and there's a port A here, there's port B here, port B here. But for things like VDD and VNW, it shorted them at a higher level. Then we run LVS on this thing. It can happen also when we connect things at the board level. So if we took A and B and for some reason they were going to be shorted together on the board level, but we didn't want to do it inside, again, we could mention it here as these two things are connected together at the wrapper level instead of doing it with the star.connect statement. So after looking at the problems that we had with converting our Verilog netlist to SPICE, I want to show you some of these things as examples. So here we have our Verilog netlist that we exported beforehand, Leo1 top physical, and this is the Leo1 top module, and I want to show you that we have no more assigns in the design because we were able to get rid of them. So let's search for assigns, and we see that the pattern is not found, so there are no assigns in the netlist, and this is something that was quite important to us. Another thing we wanted to see, we wanted to look at the includes file. So we have in another window here the includes file open. So in the PDK told us we needed to add this source added file. For standard cells, we're pointing at different standard cells over here. SRAMs, different SRAMs that we compiled, and different IPs that we compiled down here. So these are all the SPICE or the CDLs of these different files that we have in our chip. Okay, so that is the includes file, and after seeing that, we can now go to run v2 LVS. So So we're going to run v2lvs, and as you can see here, what we're going to do is we're going to add this minus add pins vnw vpw, and we're going to put our includes file in it. And so let's do the run, and you see it gives us all kinds of warnings and all kinds of things. It's mainly because of the flattening bus that we did. But finally, at the end of a very short type of a process, the script will finish with all kinds of things here again that it just complains about. But finally, what we get is that we have this Leo1 top source spice file that came out, and we can open that guy up. So this is the Leo1 top source file, and one of the things that we can see here, if we go to the definition of Leo1 top, we can see that it added actually already here VNW and VPW ports, which were not in the original Leo1 top, and then it added to each and every like standard cell or whatever that's inside these VNW and VPW ports inside the netlist. So we have that worked, and just one more thing, I told you that we can make a wrapper. Okay, so I'm gonna open up the wrapper. So here is the wrapper of Leo1 top, and basically all it is just includes the Leo1 top source that we just made, and it has the port definition. There is no VNW or VPW in the source definition, but then it instantiates our top level that we read in through this spice file over here, and you see it just connects each and every one of the pins to itself, except for when we go down and we look for things like VNW is now connected to VDD and VPW is connected to VSS. So that's kind of how we take care of that, and that's the wrapper we run it on. We have the same wrapper for the layout, so this is the layout wrapper, and again it instantiates what we're going to extract, which is the layout netlist, and in this case there is no VNW VPW, so we don't have to put that in, but it has other things that it might be instantiating. So we run LVS between the wrappers. So that's kind of what I wanted to show you in this section, and now you can continue to the next section where we're going to extract our layout netlist.